So you can probably teach me a few things in terms of programming. So I don't need to cover any like how programming works. We can just
No.
focus on the smart contract stuff. Um, so in that case, then I guess the best place to start in terms of what you're comfortable with is like how about some of the blockchain stuff? So do you feel like you have a good idea of like how proof of work works, for example, like mining and stuff like that?
Yeah, I have a pretty good idea that it's strong cryptography, and somebody gets elected to create the next block, and they earn um, well, not Bitcoin, but I guess it's gas and Ethereum for doing the mining, right?
Yeah.
I have some things I don't understand, like I assume it takes gas to run a smart contract, and I'm not sure how that's acquired. If I were to develop a smart contract, how would I go get the gas for that smart contract to run?
Yep. So gas is a good place to start. And then the only thing I'll mention before that is like, so different blockchains have different characteristics, right? So you mentioned something about being elected to produce a block. So a lot of
Right.
blockchains work like that. So for example, the EOS or EOS, this new blockchain that just launched, which has like a proof of stake system that's with voting and stuff. So they have this like election process for deciding who gets to create a block. But so systems that are pure proof of work systems like Bitcoin and for now Ethereum, the way that theirs works is that people are just guessing hashes basically. So and you have to find a hash that's valid. And so if you're taking all the data, all the transactions and the smart contract code and everything that people are sending to the nodes, and you're trying to package them up in a way that produces a valid hash. And so you manipulate the data, you calculate a hash. If it's valid, then you win and you broadcast your block. And if you don't, then you just keep guessing. And so it's basically a race amongst all the miners to produce the first block. There's no election or consensus on who gets to. It's just people racing against each other, which is why you have like this whole thing about ASICs and the energy usage keeps going up and up and up because people are just competing against each other.
But is there a potential for a tie in that situation?
Yeah, great question. Yeah, very good question. So there is, and so if you have a tie, so you have two valid blocks, and they might propagate throughout the network at different speeds. So some nodes might see one block first, and some nodes might see another block first. So the way that Bitcoin resolves that is if you have competing chains, the nodes, by consensus, will go back to the chain that is the longest, that has the highest
okay, I did read that. Okay, I remember now. Yeah.
Yeah, and so sometimes, like if you've ever like done a Bitcoin transaction or like done anything on an exchange where they make you wait for a certain number of confirmations, like a certain number of blocks have to go by, that's actually the reason that they're doing that. They're trying to make sure that your transaction didn't end up in an orphaned block on some chain that didn't get
On
included.
an orphan chain that lost the race. Okay.
Exactly. Yeah, that's exactly right. And so
Thanks.
Ethereum actually has like a even more advanced system than that, where it's called Ghost, I think it's called, where they actually consider for the miners rewards some of the work that they did for the alternate chains. But that's kind of an implementation detail. It just allows Ethereum to have faster block times than Bitcoin without running into these issues. So so that kind of makes sense, right? The next thing to talk about then is probably gas and how smart contracts work. So with Bitcoin, it's just like you send out transactions, right? So the only thing you can really do on the Bitcoin network, it's a little bit of a simplification, but for the most part, when you're on Bitcoin, what you can do is you can send value between people, right? And Ethereum lets you also send code that can be run. And what the code does is so when you send code, when you tell a node to execute some smart contract code, what they basically do is they run that code, and then that code gives them the final state, and that state is the thing that they include in the block that they're going to mine. So they have to execute your smart contract code to determine the state and then include that state in the block. And so because of that, obviously, you have to have some kind of limitation because it's a full Turing complete programming language. It could have an infinite loop. It could go on for a very long time, and no one could determine that. So that's where gas comes into play. The basic idea of gas is that it puts a limit on how much computation your smart contract can do. It also signals to the nodes, the miners, how much you're willing to pay for the computation that is that you're asking it to execute, right? And so they can decide whose code to execute based on who gives them the best rate for the gas. And so you ask, like, where do you get gas? You actually never have gas, right? What you do is you say, here's the amount of gas that I want to use in this transaction, and here's how much I'm willing to pay per unit of gas in Ethereum fees.
Okay.
So you send that out with your transaction. You say, I want to use 300,000 gas, and I'm willing to pay, 0.000001 Ethereum per gas or whatever, and then the miners will either say, okay, that's a good deal, that or they won't, right? And then they'll execute your transaction and spend that gas. But it's a little bit confusing because you never actually own any gas, and other blockchains do that differently. Other blockchains have a separate token specifically for this concept of gas.
So if you are the author of a smart contract and you want that smart contract to be executed, you don't own gas, but you do need to provide some amount of Ethereum for your smart contract to execute, correct?
Yeah, so actually, this is another good point. So the smart contract, the gas is paid by the person who's calling into the smart contract, not the author.
Okay, not the developer, but the person who's going to use that smart contract.
Right. So at the time, so if I'm buying a CryptoKitty, right? At the time I buy my CryptoKitty, I have to provide the Ethereum to buy the CryptoKitty, but I also have to provide a little more for the gas that executes.
So think of it as a transaction fee. Okay.
Exactly right. Yep. That's literally what it is. It's a fee that you're paying for the miners for executing your code and storing the state in their block, basically.
Now, I'm just going to verify something with you. I think I've read. So just like there's a JVM underneath the Java environment, there's an EVM, like an Ethereum virtual machine, right? And when we say code, we're talking about Ethereum bytecode that's sitting in blocks in the blockchain.
Exactly right. Yep, you beat me to it. So EVM is just like the JVM. The only the big difference is that it has it has opcodes and everything, just like another virtual machine would. The only real difference is that it has within those opcodes, it has some native handling of these things like gas and and addresses and things that are specific to the blockchain, right? So it has some characteristics that you wouldn't see on just a standard VM, but otherwise it's just a VM. And so every mining node has that VM, and they're going to execute your bytecode on that VM. And so because it's a VM and has bytecode that compiles down to it, you can have multiple languages that target it, right? So the language that is the most popular and the one that we're going to dive into in a minute is called Solidity. But there are actually a bunch of other languages that people have created. And I think it's probably a space that's going to get explored a lot more moving forward, because Solidity has some issues, and people are exploring things like correctness proofs and stuff like that to avoid hacks. So like languages that we may end up where the languages that we use to write smart contracts end up having very different characteristics from the programming languages we use in other circumstances. That's my guess, is that in the long run, the best practices are going to settle around languages that have things like correctness proofs and all kinds of stuff that we just don't really need in a normal computing environment, because you can always just fix the bug and update the code, So
now, if I can stop you one quick second with a question along those lines, is there the possibility that a miner in the midst of running a smart contract could run out of gas, and does it return an error to the caller?
Yeah, so if your smart contract is executing and you said, I need this much gas and I'm willing to pay this, and the miner said, okay, and he starts to execute your smart contract, and then it runs out of gas, then it does what's called a revert. So nothing that occurred will be stored in the block. No state changes will be stored. It's not like it's halfway and you have to figure out what happened. It's as if your code never run. You'll get an error back. And it'll tell you that you ran out of gas. The only thing is you don't get to keep you pay the fees.
Your transaction fee is gone.
You pay the fees regardless of whether it executes.
You use that gas essentially, so it's gone.
You burn the gas. You just ran out.
Cool.
Yeah, exactly right. Cool. So I think kind of, it sounds like you knew a lot of this stuff already, and we've touched on, I think, some of the big stuff to clarify.
I think it helped me verify some of the concepts.
Cool. Awesome. So I think at this point, let me try to share my screen, and we can jump into actually writing some code. And at any point, if I'm going too slow, too fast, whatever, just be like, just let me know, and we can adjust. And that's part of what getting some of this feedback is a lot of what I was after. And again, I appreciate you taking the time. So let me see, how do I do this?
This is great.
And caveat here is that I'm not an expert either, right? So I'm learning this stuff myself.
But you've written some smart contracts, so
I have
an infinitely larger number than I have.
Oh my God, we're in.
Oh, that was cool.
Speaking of infinite, there you go. Cool. So I'm just in Remix here, and like I said, if you want to follow along at home, that could work. You let me know how it goes, and we'll work it out. So this is the default thing that they give you. So I just created a new file. I called it hello billboard .sol, so sol for Solidity. This pragma mark at the top is just telling the compiler what version of Solidity that we're using. Let me see, get the font a little bigger, and then maybe I can also blow the browser up. How does it look on your end? Can you see things okay?
Since you that last blow up helped a lot.
Okay, cool. And let me at any point know if you want me to adjust it some more.
I did want to ask you one quick question. I followed the link myself to the Remix.
Yeah.
At one point, and it launched me like I was in the middle of editing an app, like the initial launch.
Oh yeah, did it give you this like ballot.sol?
Yes, it did. Is that just its default launch?
Yeah, it's a default thing. I don't know why they include that as the default one.
I just want to make sure I didn't go the wrong place.
Yeah, it's a little bit.
Oh, there you. I see you.
Yeah, they have it on here too. So the thing the first thing that I did was to create a new file.
Right.
And then, or you could just blow away what's in that ballot one.
And this pragma tells the network, or it's the Solidity compiler, what Solidity runtime we want to use, right?
Exactly right. Yeah. In fact, it's telling the compiler. Well, that's a good question. I think it's telling the compiler which version to use. I think once it gets compiled, it's all down in opcodes, and the VM is just going to do what it does. So this is telling the compiler what version of the language to use.
But could there be servers out there who had different versions of the runtime on them, and would that affect where this billboard program you're writing, where this smart contract could run?
Yeah, so I mean that's a problem that the people working on Ethereum have to worry about, right? They have to make sure that all the nodes have that the EVM is backwards compatible, and that the nodes run the right thing, and that kind of thing. And so if they want to make changes, they need to make them in like backwards compatible ways. And if they don't, then that's a hard fork of the network that has to be coordinated and all that stuff. So
understood.
That's not really your problem, hopefully.
Right.
Cool. So what's happening here is we have an editor, right? That's pretty straightforward. And this is where we'll write the Solidity. And then down here, you get like a console that will show you error messages and let's get that out of here. Oh my God, error messages and other stuff. And then on the right-hand side here, we want to go to this Run tab and make sure that we have the JavaScript VM selected. So when you have that selected, what's basically happening is it's running a JavaScript version of the EVM in your browser, and it's basically going to act kind of like a little blockchain that automatically and immediately mines all of your transactions and stuff for you when you are executing your code. So it's going to let you kind of like debug. It's going to let you compile your smart contract, deploy it to this fake network, and then kind of interact with the smart contract as well.
So the smart contract that you're writing here is sort of running in a sandbox then?
Yeah, it's all in a sandbox right here in the browser that's going to let you like kind of iterate on it the way you would a normal program, as opposed to having like deploy it to a test network every time or something like that. So then this is a list of accounts, or like wallets, basically addresses. So it gives you, what is this, 5 accounts out of the box that you can work with. So whenever we're going to be carrying out an action on our little fake sandbox network here, we can pick which address we want to be when we carry out that address. So it's like having 5 different Ethereum wallets that could represent 5 different users of your
Right.
smart
So
contract.
this is the role under which the smart contract is executing.
Exactly right. Yep. Cool. So then we'll come back to what else is going on over here as we start to dive into it. Here, let's see that. Clear that up. Good. Okay. So I have no compiled contracts. Let's go ahead. We'll write our first contract here. So the thing that the kind of sample project that I came up with, and I have some notes that I may refer to as I'm moving along, is the idea of a billboard on the blockchain. So the idea is you'd have a message that can be displayed, and you want to allow people to update, to view that message, but also to buy and update that message if they want to advertise for something on your billboard. So totally contrived, but that's the idea. It should give us the ability to see some basic stuff. So Solidity is a pretty, it's, a lot of people say that it's like JavaScript, which I don't understand why people say that, because the semantics of the language are nothing like JavaScript. I mean, it has some vague syntax similarities, but that's just because it's a C-like syntax. So you'll hear that a lot, but I don't get it. That doesn't make sense to me. So it's a typed language. First of all, it's statically typed, and it's what I kind of call it contract-oriented, which is basically means that it has all the kind of semantics and things that you're used to in object-oriented programming, except instead of creating classes that instantiate objects, you're creating contracts that are instantiated when they're deployed on the network, right? But you interact with them like with dot syntax and a lot of the same ways that you're used to interacting with objects in many OO languages.
Okay.
So, and that's all that I mean by that. And a contract combines like functions that can execute and state, so property. So again, very much like an object-oriented paradigm, except it's a contract instead of an object.
So a contract has private state that method calls on the contract can modify.
Yep, and we're going to get into all that. Okay. So once I've done this, how come this isn't compiling? Oh, auto-compile, that's why. So I'm going to make sure that auto-compile is checked. So once it compiles, you'll see now in my dropdown I have the Billboard smart contract available to deploy. And I have this button that says deploy. And so when you create a smart contract, once you've tested it and you want it, you have to deploy it onto the network, right? The Ethereum main network. So this is what we're simulating through this browser interface here. When we click deploy, this puts the contract onto our little sandbox network. And you see the VM gave us a response. You also notice that the balance of Ether in our contract, our account here, went from 100 to 99.9999 whatever. That's because we spent a little bit of gas deploying our contract out to the network.
Understood.
So we've spent gas to do that. And now you see down here, this little box represents the contract on the network. And you also notice that the contract itself has an address. It kind of gets cut off here, but a contract has an address or an account just like
a user.
Exactly right. Yeah. So this is the contract address. And if you were in this setting of a real network, you would want to make sure you knew that address, and you would need that to interact with the contract. That's how you tell the nodes where to go to run your code, basically, when you're working with a real deployed contract. So since we have nothing in this contract, it's just all it does is give us an address. It's completely useless. There's nothing really to do here. You'll notice that I can deploy it again, and I get a different address, right? So once you deploy a smart contract, it's there on the network in the blocks forever. You can never change it. The code is what it is, right? So that's very different from most software, right? That you can always go back and update. So if you deploy it again, what you do is you deploy a new instance that gets its own address, right? So as we work through the rest of this tutorial here, I'm going to be deploying it lots and lots of times. But just remember, actually every instance that we've ever deployed is still there at a different address and could still be interacted with someone, right? Someone could choose to interact with the old version of the contract if they wanted to. So that's important to remember. So let's delete that.
The contract itself is just residing, various versions of the contract are residing in various places in the history of the blockchain.
Exactly right. And what it really is it's just data, right? It's the bytecode.
Right,
It's the
right,
compiled bytecode that's stored in a block
right.
somewhere, and that data is then replicated on every node. And so what you do when you execute a smart contract is you're saying, go get the data stored in this block here and run it as bytecode, right? And
So is there something like a DNS for smart contracts? Because I assume CryptoKitties is a smart contract, but every time they do an update to it, I want something to find the new address of the latest CryptoKitty app for me, right?
That's a great question. So there is something called the Ethereum name service, which kind of does sort of what you're talking about. But actually, for the most part, when you're interacting with dApps, you're always interacting with the same version of the contract. And the reason is because, as we're going to see, the contract holds state. And so, like, if CryptoKitties can't just deploy a new version of their contract,
Oh,
because all the state about who owns what kitties and everything would be reset on that new version. So once they deploy their contract out, that is set, and that is it forever. Now, what you can do, I'll mention, is you can use patterns in your code that allow you to update some portions of it, right? So if you have like a utility function, you can deploy that in a separate contract, and you can have your contract have have a property that says, here's the address of the utility function that I want to go call, right? And then you can update that address in the future as state in your contract so that the logic around, so if they wanted to change the breeding logic a little bit, if they have like a breed cats function,
right.
they can point to a new breed cats function, right? But they can't just wholesale redeploy the base contract because that's what's storing all the state.
So the sort of base contract is sort of like the front panel for their CryptoKitty app, right?
Exactly right.
And
yeah.
everything behind it might be made up of lots of different components which are separate contracts that they can change in and out, but the front panel to CryptoKitties remains the same, so everybody has their maintained original state.
Right, and that's part of like your job as a smart contracted developer is to think about what are the things that I might need to update. How do I architect this such that I can update them in the future?
Okay.
And
component design is huge here.
Yeah. There's a lot of testing and auditing before you deploy because you can't change it once it's out there and in use and stores meaningful state for users.
That's very different.
Of course. Now, and of course, you could also do something where you migrated, right? So you could write a new contract.
Oh, you can pull state from the old contract and drop it into the new contract.
Yeah, so it's still malleable, but it's far less malleable than what we're used to, right? I mean, it's just it requires like a whole new way of thinking. So, all right, so we have our very boring contract here. Let's go ahead and start adding some of that state to it. So the first thing that I'll add is a property for the message. So we declare it as a string. I'm going to declare it, well, actually for now, I'll just say a string message, and we'll see what that does. So if I say string message, and actually I'll give it a value, I'll say hello world, because programmers are not creative. We end the line with a semicolon here. So, syntactically nothing unexpected here. And now this compiles, and if I deploy it now, it looks the same, right? Like even though I've added this property, nothing looks different about this contract. And that's because although I have stored some state here on the blockchain, I haven't stored it in a way that makes it easily accessible. So if I put this public keyword here, what that means is that this string property in the contract can be read by anyone. Now, it's important to remember that anything that's stored on the blockchain, any state on the blockchain can always be read by anyone. It's all there in the block. But what this public does is it asks the nodes and the compiler, I'm not exactly sure about how it all interacts, but it basically stores it in a way, it indexes it basically to make it easily accessible for someone who wanted to get it. So it basically creates a getter. You can think of it as creating a getter.
Understood.
So now when I deploy this contract, you'll notice in the interface here, I'm given this little button for the message. So when I press this message button, that's the equivalent of making a JSON RPC code call to the node, asking them for the message property on this contract. And it returns hello world, right? So if my smart contract were on the network, I could call a JSON RPC function and get this message property, and it would return hello world for me. So this is the current state of that message property that we now have stored on the blockchain, and anyone can read this. And since that's all our contract does, it's going to be like that forever. It's not going to be able to change. Nothing mutates it. Just because it's public, there's no setter, right? There's no mutation. It's just readable, if that makes sense.
Yes, but I assume contracts can have state that is mutable.
Yep, and we're gonna start looking at that soon.
And does that turn into that turns into new transactions on the blockchain?
Really good question. So we'll see how that works when we get there, if that's okay.
Yep, that's fine.
So the next thing I'm going to do is create a constructor for this contract. I can spell constructor. And I'll mark it as public, and that's it. So this is empty right now. What I'm going to do, I'm going to add a parameter to it called initial message. And basically now I'm going to set the public property of message, the property, to the initial message that will be provided in the constructor. And the constructor is kind of what you would expect it to be if you're coming from an object-oriented programming paradigm, except you have to remember that a constructor, so an object can be created in memory and destroyed, and that happens all the time. A contract, the equivalent thing that we think about with a contract is when it's deployed to the network. So the constructor is executed when the contract is deployed to the network. And that's the only time it's ever executed. So for a given instance of a contract, the constructor only ever runs once in its life cycle, which is the same as an object, but you just have to remember that that contract is then sitting on the blockchain forever, right? Which is different from an object, which might get destroyed half a second later in memory. So the constructor really just sets up the initial state of the contract. So now, when I come back over here and I see my deploy button, you'll notice that it's now asking me for a parameter. So when you deploy, you can send parameters into the constructor along with it. So again, lacking creativity, I'm going to just say foo_bar, and now when I deploy, it's going to give me an error. JSON parse, unexpected identifier. What did I do? Oh, I always do this. When you do this in this.
Oh, it's a string. It's a string variable, so it type checked it.
Yeah, exactly. So you have to put quotes. You have to put quotes here. It requires that. It doesn't. It's not smart for you. So you hit deploy, and now if I call this message getter, I get foo_bar. And if I deploy now another one with a different message, so here's another instance of the same contract, but it has a different state because we initialized it with a different state on deploy.
So now we have 3 or 4 different versions of Billboard deployed. If this were real, they'd be out in the blockchain.
They'd all be out there in the blockchain. Anyone could look at any instance of them and see the state that was there. And I keep clearing them away, but they're still there, right? And our gas keeps getting, or our ether balance keeps getting lower and lower because every time I deploy, I'm spending to buy some gas to do that. So let's now move on to, so this is kind of, we can now deploy with some state, but now let's create a function to buy the billboard. And this is public. That means anyone can call it. You can have functions that, sorry, let me silence my notifications here. Dun, dun, dun. Do not disturb. So you can have functions that are internal to your contract. In other words, they're not given an easy interface, like an index interface for someone to call external to the, from the network. But if you mark it as public, that means that anyone can call it. That makes it as part of the interface of your DApp, of your contract, basically.
Private function versus externally callable method.
Yeah. Yep. Exactly right. So here we'll do. So for now, we'll do kind of exactly what you would expect, which is, oh, I have to burp. So string new message. And now I'll say message is new message. This is not super exciting. You kind of get the point here. Hello world, can deploy it. So now you see that I have this function that I can call, and that I can pass a parameter to this function. The only thing to note is if you pay attention here, so far when you call this message value, you look at our account and our balance is not going down. So when you have state on the blockchain and you want to read that state, that's free, basically. That's just a network call. The node, I guess, has to expend some bandwidth to respond to you, but it doesn't, you don't pay any gas or do anything for that. So you can always read state from the blockchain at any point. And there's no cost associated with that. There's no transaction fee. You don't have to sign a transaction to do it. That's not the case when you want to mutate state on the blockchain. So if you want to store something like your contract code, or like in this case, a new billboard message, if I want to store that, that's going to cost me some gas. So I have to pay a fee to do that. And so you'll note that our account balance, when I execute that, is going to drop a little bit. And so now if someone were to come along and call this message function, so I'm going to press the button to call it, they're going to get a new value out for the state of the message function, or the message property in the billboard. So one thing that's important to remember, though, is that we've updated the state. The blockchains are immutable, right? So everything that's stored on a blockchain is always there forever. What we've done is we've updated like the head state of this value. So if someone asks for this property, they're going to get that back. But if someone wanted to like go back and download the blockchain data and look throughout its history, they could see the value of that property at any point in the past as well, right? So it's not like you're deleting or overwriting something in memory. You're just updating the latest value. All the other values are still stored in the history of the blockchain, if that makes sense.
Understood. So it's sort of like every transaction all the way back to the beginning of time is there.
It's literally exactly like that. Yep, they all are, yeah.
Now, are we missing a parameter from our buy billboard function?
Yes, we are,
Okay.
right? To pay, right? That's
right.
That's what you're thinking of?
Yes.
Yeah, exactly. So right now, so let me show you something that's important, Rich, is right now we've been doing everything from this first account. So if I switch to this other account, so now I'm acting as someone else, I still am able to come in here and, update the message and read the value. Yep. And so if you were to deploy this, anybody who is willing to pay the gas fees would be able to update the state property of your billboard for free, basically, just for the fee that they pay in gas.
Right.
So obviously we want to fix that. Now, the way that you do that is by marking the function as payable.
Oh, okay.
So this is another modifier, just like public. So it comes after the function and it says that this is a payable function. And a payable function can receive value in Ether. And the way that you do that in this interface in the Remix IDE is right here. So if you want to,
I was wondering what that parameter was. Okay.
Yeah, so here, this has been our gas limit all along, right? We just leave that alone and it's going to handle it for us. But this is when we call a function, that is payable, we have to first say what value, in other words, the number of Ether that we're sending into the contract. Have you heard of Way before?
How's that? Sorry. I may have. How is that spelled?
This word right here, W-E-I.
I've seen it in papers and stuff.
Yeah, so Way is the smallest unit of Ether. So it's kind of like
a fraction of Ether, a fraction of 1 Ether.
Exactly. So it is it's the smallest fraction of an Ether. I'm forgetting actually what it is. So each of these is a thousand.
Is a fraction of a finny, a G-way?
A G-way, a gigaway. So each of these is a thousand, 3 orders of magnitude. So a finny is 1,000th of an Ether, a gway is 1,000th of a finny, and a way is a 1,000th of a G-way, a gigaway. So whatever that works out to, 10 to the minus 18th or something, I don't know off the top of my head. That's what a way represents in Ether. And when you work with a smart contract, so, as a programmer, when you work with money, you always want to store it as an integer, right? You don't want to store it as a float. And it's the same way with the EVM and Ethereum in general. So when you store value on Ethereum, what you actually store is an integer, a 256-bit integer to be specific, representing the way that you have. So when you say that I have an Ether to the network, what that actually means is you have 10 to the 18th or whatever the number is way stored in your balance. So anytime you're working with value inside a smart contract, you're working with way. And it provides nice ways to deal with that, as we'll see. And so you're not using huge numbers all the time, but the base value is always a uint of the way that you're dealing with, an unsigned integer, 256. So this interface lets me just update that to Ether. And so now I could put 1 Ether here and buy this billboard by paying the Ether. So let's see what that. So let's do that. It won't really. Actually, hold on. Did I deploy it? I don't think I did, since I updated it. So let's get rid of this guy. Hello. We deploy it. It fails. Oh, it's because I had. So see what happened? I had a value set in that.
Right, and when you blew away the deploy, it removed the value.
So I tried to call my deployment. I tried to do the deployment and send value with a deployment, which doesn't make any sense. So then, so it's saying, what are you doing? Don't send Ether while you're deploying a contract. So okay, get rid of that and deploy. And now my contract's out there. So now this interface isn't great, but what this means is if I set that to 1, the next action that I take is going to include 1 Ether along with that action, with that send, with that function call. So now I can say my new message, and I can buy the billboard, right? The thing is, we haven't set anything here that says like what we're charging for that send, right? So anyone could send anything that they wanted. They could send 0.001 Ether, and it's going to work without any issue, right? As long as they're paying some value, it's gonna work. So we want to put something in our contract that only allows them to update the billboard if they pay what we've decided is an equitable fee. So there's a statement in Solidity called a require statement. So I'm going to say require that so there's a concept of a message. Let's cover this first. There's a concept of a message inside when you're executing a function in Solidity. You have access to this global property called message, and this is basically the message that was sent, the function call, to the function that you received, right? So it stores information about what the user who is calling this contract sent, the message that they sent to you. So one of the things that it has is the value that was sent along. So if I come over here and I say 1 Ether and I call this with 1 Ether, inside my function, my message value is going to be 1 Ether, or 1 times 10 to the 18th way, or whatever it is, right? So I can say require that my message value is equal to, logical operator, 1 Ether. And here is where you see there's this nice native keyword.
In the native unit.
Yeah, native unit. So when I say 1 Ether, internally what this does, probably it's just a compiler operation. It probably doesn't even show up. It shows up as 1 times 10 to the whatever. So it does that natively for me. So it's just a nice keyword. And then I can also...
Can I stop you with a question real quick?
Anytime.
Okay, so because this function is payable, then the message has a property of value. If this function, I assume public functions that are not payable, they're still invoked via message. Would value not exist if it wasn't a payable function?
That's a great question. Off the top of my head, I'm not sure if the value would be like null or if it would be 0. Very good question. I don't know.
I'm just
could try it out
distinguishing between payable functions and normal functions.
My guess is that it would be 0, but I'm not 100% sure. That's a good question.
Like, would you get an undefined in Solidity if you went message.value? Would you get an undefined at runtime if you referenced message.value?
Yeah, I don't know if you get it at runtime. I don't think it's a compiler error. Let's see. So let me fix that. See if this will compile at least. Yeah, it looks like it compiled. It gave us a warning because we didn't do anything. Oh,
Right.
look. Message value used in a non-payable function. Do you want
Ah,
to add
okay, good.
payable? So it knows, it
It
allows us
figured
to
that out.
reference
That's
it.
nice to know.
Yeah, cool. So it'll at least warn you about that. And so the require function, and this is actually new in the latest version of Solidity, allows you to also provide a reason why if this
Oh,
fails.
that's excellent. So the caller can be instructed what went wrong when
Yep,
the
so I can say
require fails.
did not pay billboard fee.
Right. Very cool.
So now if I'm going to blow this old one away, and I'm going to deploy this out. Hi. Now I'm going to come over here and I'm going to say 0.5 ether, and I'm going to say hello world.
He's going to say you can't.
Yeah, and so now this will fail. So
And where
transact to
did that
billboard.
failure show up? Oh, it's in your log. Okay.
Yep, so I can see it down here. It says it reverts. So reverts means that no state has changed on the blockchain except you paid your fee. That's the only state changed to the blockchain. So you
Now,
lost money, but
the
that's it.
address that attempted to execute the contract,
Yes.
how does this come back to him that he can, like another contract attempted to execute this contract, right? Possibly.
So in this case, the user, the account that's trying to execute the contract is a regular old user wallet account.
Right.
So in that case, what would happen is the user, whatever context the user is in, so if they're like, sitting at the command line banging this out, then they're going to see some error come back from the node. If they're in a dApp, then the dApp is going to get that behind the scenes, and they can decide how to display it. But that's what's going to come back. So another contract can call another contract. If the contract that you call to reverts while you're running, the whole thing blows up, right? So you don't get to know that it failed as the parent contract that called the subcontract.
Really?
You're just dead, right? Because it's all considered one like execution, right? So it's just going to show back up as a failure to whoever tried to execute the contract. It's not going to, the calling contract won't know that something that it tried to call blew up, if that makes any sense.
Yeah, it does. But how does the ultimate user then get notified that a fee wasn't paid and something needs to be changed?
Yeah, so the node is going to respond to whoever's talking to it, right? Over that JSON RPC interface, the node is going to respond saying, "Hey, something went wrong. We reverted." So your dApp or whatever context you're interacting with this smart contract is going to know that it reverted. But all I was saying is that if you're a contract calling another contract and that contract blows up, you are not going to be aware of that fact. You're not going to know it. The whole execution on the EVM either has to succeed or it fails and blows up and bubbles back up to the caller of the initial person who executed the transaction, if that makes sense.
But
external to the network.
Is the error message that we've put here on the second parameter of the require, does that bubble up?
Yeah, good question. So yes, the short answer is yes, it should. The longer answer is because this is such a new feature, actually some of the tooling doesn't do it yet.
Okay, we're
but it
bleeding
will.
edge here. Okay.
Yeah, we're bleeding edge.
Okay.
So, but you see that it shows up here, like down here in this little console. That's kind of the equivalent thing. Like if we were interacting with the network and we did this, like the network would respond and it would say reverted because did not pay billboard fee. But the point is it's external to the network at this point. Like once something reverts, it goes back up to whoever asked the network to run it. So we put this require message here, and we've now set our Ether fee. We've just hard-coded our one Ether fee. So now if the user wants to update it, they have to pay exactly 1 Ether. So if I come over here now, so right now the message is still high because that's what we deployed with, and we did not pay the fee properly when we tried last time, so it failed. If I now come over and say, hello world, nope, hello world, and I pay exactly 1 Ether, now it will succeed. And now if I look at that message property, it's been updated.
Right.
So that's good. Okay, so the require statement basically says if this isn't true, I revert, I fail, and with this message, and no further code is executed, and any state that was changed up to this point is reverted. That's just that's how that works, and it's important to understand.
Right. Very cool.
So so this is good. I'm debating whether to go to. I'll skip. Yeah. The next thing I think that we might want to do is allow ourselves to update the fee that the billboard costs. So let's say no one's buying our 1 Ether billboard. We want to lower the price.
Drop the price, right?
But right now, we don't have a way to do that, right? So we've deployed this contract. We hard-coded this value. That code is set in stone forever and ever. So we have to deploy a new billboard and get people to use the new contract if we want to do that. So if we were architecting this from the beginning and we were smart, we would say we want to be able to update the fee. So we'll say a uint, and you can specify how many bits you need. Since this is we're dealing with way, and it needs the full 256.
Right, because it's currency.
Yeah, and so actually, what you can really do is just say uint, and leave the 256 off, or you can make it explicit. It doesn't matter, but the default
to the 256.
Uint is basically just an alias for uint 256. Okay. You can think of it that way. We want it to be public because we want people to know what the fee is, so we want them to be able to read that value. And I'm actually going to call it cost instead of fee because I don't want to confuse it with the network fees that are being paid.
Right.
So I'm going to change the name here on us. So I'll update that to reflect that. So then in here, we'll say string initial state. I could provide an additional parameter that said initial cost. What I'm going to do is I'm just going to hard code it for now, mostly because I don't want to have to type it in every time I deploy it. But you could allow that to be part of the state that got set when you deployed it. So I'll hard code it. And then down here, instead of looking at my hard coded value, I'll update this to say that this is the cost. And the last thing that we need is a function that says update cost. We can just call it set cost. Naming. And so it takes a uint of new cost, public, because we want to be able to call it externally from the network into the network. And it's not payable. We don't need to set value for this. So now cost equals new cost. All right, so I think that is everything that we need to make the fee updatable. So blow the old one away and deploy it with hello world. Cool, so now when you look down here, we have some new stuff that showed up. We can get the message. We can also see the current cost, and you see how it's displayed. We set it as 1 Ether, but the real value is this huge number, right?
Yeah, it's a huge number of way.
Exactly right. Yep. And so now, if a user wanted to buy the billboard, right now the fee is that number of way, which is 1 Ether. So I could come over and I could say bar, set my value to 1. Buy the billboard, succeeded. So there's my message. But now let's say we're not getting enough usage at 1 Ether. We want to lower the price. So we can come over and we can say the cost is now. So this is in way. So I have to provide the right number of way. So that's 1 Ether. So if I take off a 0. Take off a 0 from the end and change this to 5. If I did that right, that should be half a way. So if I set cost and then look at the cost, that looks right. Now, if my user comes over and says, I want to pay 0.5 and Fubaz, they can now buy the billboard, and it works.
Okay. 1 or 2 questions here. So first of all, set cost looks like anybody could call it. So if I wanted, right now, if I wanted to spend, just a single way for this billboard, I could make my own call to set cost, set the cost to 1 way.
Yes.
Okay.
I was wondering if you would catch that. That's exactly right. I won't go through the exercise of doing it because you recognized it already. But if I were to switch to this account, I could first call set cost, set it to one way, like you said, and then I could buy the billboard for one way. So we obviously need to resolve that. Great catch. Awesome that you noticed that.
Okay, so another thing is that in buy billboard, our logical operation is equals. So if I came in with two-way to buy this billboard and your cost was set to one-way, this function would fail.
Yes.
So we probably want that. We should always take extra money, right? So we should probably set the logical operator to greater than or equal.
Yes, you could do that, right? And that's just that exactly right. You could choose this to be greater than or equal.
Charity, we'll take the extra money if you don't.
Yeah, you could do that. I mean, you might want to be nice to your users and say like, "Oh, you've paid too much," you know.
Right.
But if
we're not detecting that. Well, I guess we are, but we would actually. I guess the language has if statements or are
absolutely.
Are requires. Is there a hierarchy to requires? Could I have another require statement that said if message.value is greater than cost, then send back a message that I'm being nice. You sent me too much, so this fails?
Yeah, you absolutely could do that.
There is a hierarchy to the require statements?
Yeah, so you could just use log.
If. Okay.
Right. So you could say, so if we said if message dot value is greater than or equal to cost, and you could say, what did I do here? Oh, sorry, writing too much Swift.
It is very much like JavaScript, and it wants the parentheses, right?
Yeah, sorry. And so then I could say, so what I would actually do in this case is I'd probably throw, right? Because I know that I've hit this parameter, and then I could say throw with a message of did not pay, or
oh, okay. So throw is the equivalent of the fails side of the require?
Exactly, yeah. So okay. a require throws if it doesn't meet that.
Right, but you could just throw yourself based on the results of your if statement. Okay.
Yeah, I actually don't know. Maybe they haven't implemented. Interesting. It gave me
because the reason is a new feature?
Oh, sorry. I'm forgetting.
So revert?
I forgot that they have a new one now called revert instead of throw. You're supposed to use revert instead of throw now.
And then you can pass a reason.
Yeah. So
understood.
You paid too much. And then you could say else if message.value is less than cost. Revert did not pay billboard cost. Yep, great question. And then otherwise we can continue.
But then you can get, if you're continuing, get rid of that require, right? Okay.
Yeah, we can get rid of the require. Yeah, exactly right. Ooh. So now this would do what we want. So it should work if it's exactly equal to the value. Otherwise, it's going to send a tailored message back to our users. Now, one thing to consider here: every step in your contract costs gas. So the more logical operations that you're carrying out, the higher the fees are that has to be paid. So you're doing an if statement here. You know, as programmers in 2018, we're used to not even thinking about the cost of an if statement, right? Like, why would you even, like, if I can make this a little bit nicer for my users with this if statement, of course I would do it. You know, it's going to cost, like, with branching, it's literally free, right? Like, it doesn't cost me anything. The processor does it for me for free. That's not the case here. So this would actually increase the fee, your gas fee, a little bit. And so you can look up how much each operation costs, and you could determine how much gas this would cost, or you could just run it a couple times and see the difference between with or without it.
You would think that Remix would have something over on the right-hand panel that would tell you this contract. Well, I guess no, then it would have to actually execute each path through the code, so never mind.
Yeah, but you would think it would tell you, like when you call something, you would think that it would give you a clear execution of what your gas fee was. Does it tell you down here? I don't remember if it tells you down here. Yeah, but so the point is that this would cost gas. So if this is just a nicety, right? Maybe you don't want to actually do this logic here in your contract. Instead, maybe what you want to do is you're going to have some kind of program interfacing with this contract, right? You're going to have like a front end or of some kind, right? And what you want to do is if it reverts, then you look at the value that the user passed in and you say, oh, the reason it reverted must have been because they paid too much. Now I'll give a nice message to my user. Right. So you might want to move that logic out of your smart contract. You kind of look at your smart contract as, what are the things that I absolutely need to guarantee always execute a certain way, right? What do I need to be trustless and immutable and on the blockchain forever? And what can I do externally and still provide that value to my users? That's kind of the thing you have to think about.
So where you can do something like this in a front-end web app or a mobile app, you would do it there. The additional logic should be done there, because the logic done inside Solidity is going to cost gas.
Yeah, so every time your user runs to buy the billboard, now they're going to have to pay a little bit more to do this check, just so they could get a nice error message if they screw it up, right? And you could provide that error message external. And really, like, so you're going to have some kind of front-end app that the user is interacting with, right? What you could do there is you could, prevent them from even submitting and attempting the transaction unless they are sending the right amount of gas and the right amount of the right fee, right? In fact, you almost certainly want to do that, because you don't want to set your users up to be paying fees on gas only to find out that there was something wrong. And so your front end,
yeah, you really want to check all that external to any Solidity transactions that are going to cost.
But your DApp should prevent your user, if you've done your DApp perfectly, right, your user should never get a reverted transaction, because your DApp should prevent them from ever submitting a transaction that's going to be reverted. The reason, though, that you still have to have these things is because anybody can call the functions, right? And they could write their own, they don't have to go through your interface. They could write their own program to interact with the blockchain and execute this. And so you need to protect, really what you're doing is you're protecting from a malicious user who would try to buy the billboard for less, right? Or something like that. So you want certain properties to be guaranteed and enforced by the blockchain, but from a user interface standpoint, you're probably going to be ensuring your users never get to that point, right? Like if your contract reverts from your user executing your DApp, that you probably did something wrong. Like you should probably fix that in your DApp, right?
When you say executing the DApp, you're talking about a DApp that sounds like it's separate from the Solidity contract.
Yeah, exactly right. Yeah.
And I may not know what that is, so can I bother you to explain that?
Yeah, good question. So as I've kind of alluded to a number of times, like you deploy this out to the network, right? Your smart contract is now living on every node, right? And you can ask a mining node to execute your contract and include the updated state in their block. The way that you do that is by speaking in a JSON RPC interface to the nodes, right? So you connect to a node and you say, hey, I want to call this function. And the way that you do that is by sending a bunch of JSON to the node. And then that node is going to respond to you. When it's done, it's going to respond to you with some JSON about what happened. You could ask the node for state. So you could say, hey, node, what's the current state of my message, right? So that's all living on the blockchain. The way that your user is going to actually interact with it is through some other piece of software that you're going to provide for them. So the most common way right now, so for example, what CryptoKitties does is you do like a web app, right? In a browser using an extension, something like MetaMask. Have you heard of MetaMask?
I have not.
Yeah, so this is like a whole nother can of worms, but I can, oh my God. So if I open up my browser here, I can show you, this is the MetaMask. So right now I'm on a test network, the Robson test network. So this is like an in-browser wallet. And so if I were to execute something, so there's a JavaScript library that will allow you to talk directly to the network, right? And under the hood, it's using this JSON RPC interface, but you can just do it with JavaScript. So you can present a web interface to your user, interact with the network on the behind the scenes, and then if you want the user to execute some kind of request that's going to require a transaction, so if they're going to update state or send value, this JavaScript library, in conjunction with an extension like MetaMask, will then prompt the user to sign the transaction using their wallet here that's built into the extension. So that's the most common way, but it's not the only way, right? Like you could, in theory, you could say, I want to do something totally different. I'm going to handle transaction signing and wallets and all that stuff myself, and I'm going to write my DApp as a desktop or a mobile app or something like that, right?
I was just about to ask that, so you could.
Yeah, and at that point, you're interacting directly with the. You're interacting directly with the network, but you.
And you're pushing signed JSON over the network in an RPC.
Yeah.
Okay. But you could probably use that JavaScript library, say, in a React Native app.
Yeah,
right?
You could, or a node. back end
Right.
that powered something else or whatever. Yeah, you absolutely could. Yeah.
Okay.
So, but you just have to remember that you're going to have to deal with like transaction signing and some kind of wallet interface, and the user's going to have to fund their wallet and all that kind of stuff, right? So the UX around this stuff is really bad, and right now, like it's not ready for average users to interact with, really, if we're being honest. And MetaMask is probably, and these other browser extensions that do the same thing, are probably the best option that you have right now in terms of providing that user interface that someone can like kind of take off the shelf and interact with. But yeah, so let's I think we can wrap up here with one more thing, which is to handle the other problem that you mentioned, which is that right now anyone can set this cost.
Oh, right.
So I'm going to kind of fly through this. Tell me if anything is confusing and I need to slow down. So the first thing I'm going to do,
I'll just yell if I'm
yell if you're lost. So the first thing I'm going to do is add another property here, and I'm going to call this property the owner. So this is the owner of the billboard, okay? And the type, you'll notice, is a native type, a primitive type called an address. So this is just representing my account, my address for my account. And what it's actually storing is the full string of my address. But this is saying like this is an address on the Ethereum network. It could be a contract, or it could be a user with a regular wallet. So now, in my constructor, I'm going to set the value of owner to be equal to message.sender. So this is the person who is sending the message. In this case, the message is the deployment of our contract.
The person who's doing the deploy, exactly. Right?
Yep. Okay. So whoever deploys this contract is now the owner of the billboard. And then
down in set cost, only the owner can be the guy who got it.
Exactly.
Very cool.
Message.sender equal to owner. Otherwise, nope, you can't do that, right?
Get out of here.
Yeah, exactly. So now this will not allow any random user to do it. The last thing that I'll show you is that, so right now we've been kind of putting these require or revert statements straight into our code. There's also another way to do this, which is called a modifier. So I can say modifier is owner. And the reason I might do this is if I wanted to reuse this modifier across multiple functions. So say that I had some other state that only the owner was able to reuse, or only the owner was allowed to call. I can say is owner. I can put this require statement here, and then I can put an underscore here. And you can kind of think of this as a compiler directive, or like a compiler, oh God, my brain. Like a macro, in a sense, right?
Right. And so this then applies to all the public functions of.
I can now add this as my own modifier to the end of set cost.
Oh, okay.
So now set cost has this modifier that says is owner.
Very.
So the way you can think about this is when I call this function, what I do is I take the function body and I put it down here where this underscore is. And so I'm going to call the function, I'm going to plot the function body in here. So the first thing that's going to happen is this requirement statement is going to, this require statement is going to execute. If it fails, then the whole contract reverts and nothing happens. And if it succeeds, then the function body executes, so the cost is going to get updated. And so
right. So the underscore or semicolon represents the function body in which the macro or modifier was used.
Exactly. And so if I wanted to do some other protected thing, right? And I could also say this one is owner. And so now whatever I do in here is only going to be, executable. The owner can do this, right? So now these are both using the same logic through this modifier. And that's the last thing that I wanted to kind of show was how to create these custom.
I know we're over time, but if I could bother you with 2 questions.
No problem. Yeah, we started a little bit late, so help you. By all means, go ahead.
So question 1 is more of a compiler. I'm a bit of a compiler geek, and it seems to me there's something missing in the language.
Okay, what's that?
And that is when we go in with set cost, it sure seems like rather than uint 256, a data type that represents ether would be better here, because then as a parameter down in the I'm pointing, but in the lower section in the right hand pane where you call that cost, you had to do a calculation to figure out what the cost of, you know, half of what we were getting. But if we had a data type, and then of course Remix knew about the data types in Solidity, and the data type was Ether, you could in fact have set this based the way you did above, where you set the value to be 1 Ether. Or is that, am I off base here? Or could Solidity use a data type that represents Ether value?
Yeah, I mean, I could kind of see that as well, right? Like I could kind of, I don't disagree necessarily. Like it's a little bit weird that you have to like think of
it was odd that you had to run through that calculation in your head.
Now, externally, like if you're building a front end, right, like you're probably using some kind of library that allows you to interact with. And so that library probably, like the Web3 library that I was talking about before, Web3.js, the one that interacts with MetaMask, right? So that library has functions built in for converting way to Ether and other way around.
Right. Okay.
But you still have to think about it. And yeah, I actually think that this would be a little bit more expressive just as a language if this said something like that.
If you could say this is an Ether
and that could just be a type alias for uint 256. But to me, that would be a little bit more expressive. And so now when I looked at this, it's not like it's some random integer. It's like this is an Ether value, right? And it could do some type checking to make sure that I didn't assign a random integer to something that I meant to be Ether, right? I'm not sure why they didn't do that.
Or maybe a future version.
Yeah, it could happen. Yeah.
So my second question, you may tell me it's probably, you know, another session. Your answer might end up being long, but so you've sandboxed all of this. I've built a smart contract. I've figured out all of my interactions. What do you do to go from here to getting it actually out on Ethereum in the blockchain?
Yeah, great question. So as we've kind of seen, deploying to the network is just another kind of function, another interaction with the network.
Right.
So what you have to do is you have to compile your code into bytecode, and you have to take that bytecode and sign it with your address, and you have to broadcast. You have to send a message out to a node that says, "I want to deploy this code, and here's my gas fee that I'm willing to pay." And then once they'll do that for you, and the node will return an address, right?
Now, does Remix know how to do all of that, or are there separate utilities?
Great question. So I think that Remix actually does allow you to do that. But I have never, because they keep adding on to this and it gets more and more features. But I have never done it that way. So what I've always done is I've always used the Web3 library that I was talking about before, and written like a little node script that basically does that in Node. It's like, you know, it could be like 5 lines of code basically that says, here's my address, I want to sign it with this private key and yada yada, and then deploy it and I want to make sure I save the address that comes back. So I've always done it that way. But I think now that Remix recently added the ability to deploy directly from here. I'm not sure I would suggest it because you really want to, like, probably before you deploy anything, you want to have this Solidity code somewhere that you have unit tests wrapped around it, and you want to audit it. You want to deploy it to a test network first and have users poke around on it because of how immutable it is once it's out there. If this is a serious product like that you're launching, you probably, like, the deployment step and writing a little script to do that is probably the least of your worries, right? But
cool. Well, this has been great, Ben. This is this covered a lot of gaps in my knowledge.
I hope it was useful. You were an excellent student. You were way ahead of the curve. It was very easy to explain things to you, so I'm glad to hear it was useful.